Hey, this is Dr. Walker. Let's take a look at the second example from video 59C on work and energy. This is the outward machine that we talked about in the video, where we have two masses connected to this pulley, but we don't ignore the mass of the pulley. The pulley has a radius r and it has a moment of inertia I. The string doesn't slip, the system is released from rest. We want to find a translation speed, or v, of the blocks after block 2 descends through a distance h. Now we know that they're connected, so they're going to move with the same speed. If m2 moves down by h, then m1 is going to move up by h. So we identify this as an isolated system. There's no outside forces, it's just our blocks, our pulley, and our earth providing that gravitational force. Let's set up conservation of energy. The trick is that we have three objects, so we have to consider each type of energy for all three objects when we set up our initial energies equal to the final energies. Initially, the system starts from rest, so there's no rotational kinetic energy or translational kinetic energy. Is there any potential energy? Well, we have to define our zero level. Now we can define a different zero level for each height. You don't have to have just one zero level. We can define a different zero level for each object. So, for instance, M2, its lowest position is down here. So that can be Y2 final. That can be the zero level for mass 2. And then the initial position, Y2 initial, is just going to be the height relative to that reference level, which is h. Same thing for mass 1. The initial height is down here, so y1 initial is equal to 0, that's its lowest position. And then y1 final is going up to a height h relative to that initial height. So notice that the reference level is not the same for the two masses, and that's okay because all that matters is the change in potential energy for each mass. For the pulley, we could say the y initial is here, but it's not the position of the pulley is not going to change. So we don't have to worry about the potential energy of the pulley because the initial energy is the same as the final energy. That being said, let's set up our equation. Rotational kinetic energy plus translational kinetic energy plus gravitational potential energy. Let's say all the initial energies, the gravitational potential equal all the final. Kr final plus Kf plus UGF. We said that there's no kinetic energies of any kind for either of the three objects. How much potential energy is there? Well, Y initial doesn't have any potential energy. Neither does the pulley. Only mass 2 has potential energy. So we can say M2G Y2 initial. That's the only type of energy that we have to begin with. That's going to be converted to rotational kinetic energy of the pulley, to translational kinetic energy of both masses, and to potential energy of mass 1. So the rotational kinetic energies is just going to be for the pulley, 1/2 I omega final squared. The translational kinetic energies is going to be for mass 1, 1/2 m1 v final squared, plus m2, 1/2 m2 v final squared. Notice we don't have to put v1f and v2f because they have the same speed since they're connected. And then we said for the final potential energy, only the y1, the mass 1, has that final height. So m1 g y1 final. So when you think of it this way, it's not too bad. Just think of one term at a time, one object at a time, how many terms that we end up having to have. So we end up having 5 terms here. Now we need to solve for VF. But we can't just get VF by itself because our answer cannot be in terms of omega F because omega depends on V. If you remember, when you have an object that's rotating here, we know that V equals r omega. So its angular speed is equal to v over r. R is the radius. In this case, it's capital R. So we have to write omega in terms of v, and then we can solve for v. So let's do a few steps at once. Let's go ahead and move the potential energy over to the left side. We're going to have m2g y2 initial minus m1g y1 final equals 1/2 I. We're going to put in v over r here, so v squared over r squared, it's vf. And then over here, we can go ahead and combine these terms. 1/2 m1 plus m2 vf squared. Let's keep making more substitutions. Let's go ahead and put in what we know for the heights. Both heights, y1 final and y2 initial, they're both h. So we have m2 gh minus m1 gh. And then over here, let's factor out the vf squared. Vf squared times 1/2 I over r squared plus 1/2 m1 plus m2. We're almost there. Now we want to go ahead and solve for vf by itself. So we're going to have to take this side here. We can go ahead and factor out the gh. gh times m2 minus m1. And then we're going to divide by all of this. And in the denominator here, we can go ahead and factor out the factor of 1/2. So 1/2 times I over r squared plus m1 plus m2. So finally, we can go ahead and take the square root of both sides. And we're going to get vf is equal to gh times m2 minus m1 divided by 1/2, which we can bring the 1/2 to the top and just make it a 2 here, multiply by the reciprocal, I over r squared plus m1 plus m2. So that's our final answer because we're not given any numbers. But in general, the final speed of these masses is going to depend on the moment of inertia of our pulley. So if it was a solid disk, we would put 1/2 mr squared in there. And that is how we use conservation of energy for the Atwood machine. I hope that you enjoyed it.